Okay, so welcome back to this next video in which we are discussing cyclic groups and cyclic subgroups. Okay, right, so in the previous video what we did is we looked at the case where a cyclic subgroup ends up being infinite, okay, and those form infinite cyclic subgroups which are isomorphic to the infinite cyclic group of the integers under addition. Okay, what we're now going to turn our attention to is the finite cyclic subgroups, which are going to be isomorphic to the finite cyclic groups. Okay, right, so once again, let's start off with a group here, so we'll call it capital G. Now, this group now can either be a finite group or it can be an infinite group. Remember when we were looking at infinite cyclic subgroups, we had to be working with infinite groups, okay, because you couldn't end up with an infinite subgroup of a finite group. Okay, so when we were looking at infinite cyclic subgroups, that was only relevant or applicable to the case of infinite groups. However, we're now looking at finite cyclic subgroups, and therefore our group which we're looking at subgroups of can either be infinite or it can be finite. Okay, right, so we've got our group here, capital G, okay, and what we're going to do once again is we're going to take some element which we'll assume is a non-identity element, because if you just use the identity element it's very, very boring, the subgroup that you generate. Okay, so we'll assume that we have some little x which is an element of the group that is a non-identity element to make our cyclic subgroup that we're about to generate with x interesting. Okay, right, so the notation is exactly the same, so we're going to generate the cyclic subgroup from x, basically. Okay, and what we're going to do is we're going to, once again, create the set, and the first element we're going to put in there is the identity element, so I'll put that in. Here's the identity element. Okay, so any subgroup has to contain the identity element, so we might as well get that in right away. Okay, and then what we're going to do is put in x as well. Okay, and then we're going to start putting in all powers of x, okay, because as soon as you've got x in, then you're going to need all of the different powers of x, because you can just compose x with itself, okay, to get x squared, and if you don't have the answer to that, then of course this isn't going to be closed, and therefore it's not going to be a subgroup. Okay, so what you start doing is you start putting in the powers of x, so you'll put in x squared here. Okay, then you'll put in x cubed, okay, and you continue on as long as these powers are distinct. Okay, so if you take x squared and it ends up being one of these entries that you've already got, then you won't add it in again. It's likely not, however, going to end up being one of the entries you've already got. So it will most likely be a distinct element, so you'll end up putting it in. Okay, then you'll go on to x cubed, x composed with x composed with x, okay, and you'll ask, is that one of the elements that I've already got? So you'll look and see, is that any of the elements you've already got? If it's not, then you'll put it in as an additional element, and you'll continue on and on. However, in the case of a finite cyclic subgroup, if this is going to be a finite cyclic subgroup, then unlike in the infinite case, this cannot just go on forever. In the infinite case, we took all powers of x, and they just went on and on and on, giving us new distinct elements. Okay, so no element was ever a copy of an element that you'd already put in. You were always getting new elements, so you just have to go on and on forever. Okay, and that then generated you an infinite cyclic subgroup. If we want our subset here, which is we're going to claim as a subgroup later on, if we want it to be finite, then that cannot happen. Okay, so it has to be the case that you eventually get to a power of x, okay, which we will call x to the power of m, where m is some natural number. Okay, and this power of x is not a new element in the group capital G. Instead, it's one of the elements that you've already put in. Okay, and let's say this x to the power of m, let's say this is the first power of x where this actually occurs. Okay, so what I'm saying is that if we are generating our cyclic subgroup generated by x, what we'll have is the set containing the identity, x to the power of 1, x squared, x cubed, and you'll go on all the way up to x to the power of m minus 1, and all of these entries that you've put in so far Okay, all of these will be distinct elements in the group capital G, so none of those are the same. Okay, and then x to the power of m, when you suddenly take x to the power of m, that's where it stops. Okay, you do not now get a new element of this group here. Instead, you get one of the elements that you've already put in. You have a degenerate entry, basically. Okay, and let's say this is the first time that occurs, so all of these are distinct, and this is the first time it occurs that you're adding in another entry that you've already got, basically. Okay, right, now my claim is that if this is the case, that x to the power of m is the smallest power of x for which you are adding in an element that you've already got, then x to the power of m isn't just any old element in here, it's actually the identity. Okay, so this is an important understanding point, that the first time you get to a power of x where you're not getting a new element but you're getting an element that you've already put in, that power of x will actually be the identity. So not just any one of these elements, it will specifically be the identity. Now how can I show you that? How can I prove that to you? Okay, well we'll do a proof by contradiction. Okay, so let's suppose it's not true. Okay, let's suppose that x to the power of m is instead equal to x to the power of little n, where little n is some natural number that is less than little n. Okay, strictly less than little m. It's one of these powers here. So maybe it could be x to the power of 2, for instance. Okay, that would certainly be less than x to the power of m, but it could be any one of these. Okay, so it's some entry in here that isn't just the identity element. Okay, then what I can do is I can compose both sides with x inverse, which I know will be within the group. Okay, so I can do this as a operation on my capital G group here. Okay, so I can do x inverse to the power of n, and I can compose this on both sides. Okay, so what would I then end up with? So on the right hand side here, okay, so on this side, it's obvious what we'll end up with. We are composing, we've got little n x's composed together here, and then we've got little n x inverses composed together here. That will just all cancel out, and we'll get the identity here. Okay, on the other side, what will we get? Well, now what we'll end up with is x to the power of m minus n, and I hope you understand why that is. This says little x composed with itself m times. This says get rid of little n of those x's, because I've got these x inverses here that are going to cancel with little n of those x's that you've got there, basically. Okay, so how many x's are we going to end up with? Well, we're going to end up with little x to the power of m minus n, basically. m minus n little x's. Okay, and we know that little m is bigger than little n, so this is still some whole number, basically, some positive whole number. Okay, now why is that a contradiction? Okay, well hopefully it should be obvious. Now what we've got is a power of x that gives you the identity back again. Okay, and this power is not 0, note. Okay, little n is strictly less than little m, so this power that we've got here is not 0, so this isn't the identity. So what I'm basically saying is I am raising x to the power of some positive natural number that is smaller than little m. Okay, and I'm getting the identity. I'm getting a degenerate entry, basically. So that contradicts my assumption that I chose little m as the first power of x that gave you an entry that you'd already had. Okay, so basically what I have just managed to prove to you is that if it was the case that this x to the power of m was equal to some x to the power of n, okay, rather than being equal to the identity, okay, then I can prove to you that this m is not the first power of x that gives you an entry that you've already got, basically. There was some smaller power, namely x to the power of m minus n, which first was a degenerate entry, basically, and folded back on itself, giving you an element that was already in this subset, basically. Okay, so what I've just proven then is that if x to the power of m is the first time you get an entry that you've already put into this subset, then x to the power of m has to then give you the identity element then. Okay, right. So now what I want to show you is that if you look at all powers of x that are higher than little m, that they are also going to give you entries that you've already got in this subset here, basically. Okay, so if, for instance, we consider x to the power of m plus 1 here, okay, which is a power higher than x to the power of m, it's the next one along, basically. Okay, you might question, well, is this a new element? We know that x to the power of m is not a new element, okay, but is x to the power of m plus 1 potentially a new element? And I claim no, it's not, because what I can just do is split this into x to the power of m composed with x, okay? And when you split it like this, it becomes a little bit more obvious, because now what I can do is replace x to the power of m here with the identity, basically. Okay, and then what I get here is that x to the power of m plus 1 is just going to be equal to x, i.e. an element that I've already got in this subset. Okay, and you can go on like this. You can have, for instance, x to the power of, let's say, 2m plus 1. Okay, an element much bigger than x to the power of m. And then what you can do is then filter out x to the m twice, basically. So you'll have x to the m, and then you'll just have an x here. Okay, you can replace both of these now with the identity element, okay, and therefore this also ends up just being x. So basically, you can do this for any power of x that is higher than little m. You can just factor out as many little m's as many x to the power of m's as you can, basically, and you'll then end up with a power of x that is smaller than little m. Okay, and it's that power of x that will be one of these powers that you've already got here. So what I'm saying, basically, is that not only is x to the m a degenerate entry, but in fact all of the powers of x beyond that are just degenerate entries. So, more generally, if you have a, let's say, x to the power of a, all you need to do is factor out all of the little m's that you have here, okay, and then get a power of x that is smaller than m, basically. Okay, so let me give you an example of this. So let's say a is equal to, oh, I don't know, 49, let's say. And let's say little m is equal to 6. Okay, so if I took x to the power of 49, what I now need to do is factor out as many x to the powers of 6 as I can. Okay, well, what multiple of 6 is the biggest multiple that I have in 49? Okay, well, so 48 is a power of 6, sorry, a multiple of 6. Okay, 48 is 6 times 8. Okay, so what I can actually do is split this into x to the power of 6 composed with x to the power of 6 composed with x to the power of 6 8 times, basically. Okay, so I've pulled out x to the power of 6 8 times, and then I'll have one final x there to bring it up to 49. So all I've done is re-expressed my x to the power of 49, x composed of itself 49 times, with x to the power of 6 8 times, and then we've got one final x there. Okay, then all I need to do is replace all of these x to the powers of 6's with the identity element, and then all I will be left over with is x, basically. Okay, so that's what I mean by this. You pull out the x to the power of m as many times as you can, replace them with the identity, and then you'll end up now with a power of x that is less than m. Because if it wasn't less than m, you could just pull out another x to the m, and you'd end up with something less than n, hopefully. Okay, so you can always reduce any higher power of x, a power of x higher than m, to a power of x that is less than m, i.e. one of these powers that you've already got. Okay, right, so we don't now need to add in any more higher powers of x. Now you might be wondering about whether we need to put in the inverse elements. Well, I claim you also don't need to bother putting in the inverse elements, but we'll come on to that later on. Okay, what I now want to do then is, my claim is that this is actually a subgroup, basically. Okay, this is complete. Okay, this subset here is now complete. This is a subgroup of my original group, capital G, and this is our finite cyclic subgroup. Okay, what I now want to do then is prove that this is indeed a subgroup. So I want to go over why it's closed, and that will allow us to explore more how elements in this subset are composed with one another. Okay, I also want to go over why it's got its inverses there. Okay, some of you might be already guessing why it's got its inverses there. Okay, then what I want to do is prove that it's isomorphic to a finite cyclic group. Okay, right, so let's prove that this is indeed a subgroup of capital G then. So I'll just write it out again down here. So we've got our cyclic subgroup generated by x consists of the identity, which I might now write as x to the power of naught. That will be very helpful. Okay, then we've got x to the power of 1, okay, x squared, x cubed, and then all the way up to x to the power of m minus 1. Okay, so here is our subset, and my claim is that this is actually a subgroup if we put the inherited composition law on this from our group capital G. Okay, right, so let's go over the important axioms that this needs to obey then. Okay, so it needs to obey closure. We need to make sure that if we compose any two elements here together using the composition law on the original group, that it gives us an element back in this subset, basically. Okay, so to explore this in more detail, let's just have a look at how we compose elements together here. Okay, so if I take x to the power of a, okay, and I compose it with x to the power of b, okay, and I'll just put my composition symbol back again, okay, what is the answer to that? How do I do it? Well, hopefully again that should be pretty obvious. Okay, this means x composed with itself a times, so x composed with x composed with x a times. Okay, this means x composed with x composed with x b times. So what you should end up with then is x composed with itself a plus b times. Okay, so you just add the powers basically. Okay, now that is how you would do this if a plus b is less than m. Okay, so if a plus b is less than m, that's perfectly valid that you just add the powers together and then you'll end up with another element in this subset. However, what if a plus b ends up being bigger than m? Okay, what do you do then? Okay, well, we know how to do this. All you then need to do is factor out x to the power of m, basically. Okay, so if a plus b is greater than m, so if you end up with a plus b being greater than m, all you then need to do is say, right, I've now got x to the power of something greater than m. All I then need to do is factor this out into the form x to the power of m times some x to the power of r, where r is the bit that's left over, okay, the remainder if you like. Okay, and then all I then need to acknowledge is that x to the power of m here is the identity element, x to the power of naught. Okay, then I can get rid of that and I'll end up with just x to the power of r here, and that will then be my answer here, and x to the power of r will be one of these answers in here. Okay, because when you compose any two of these elements together, okay, and add the powers together, you can't possibly end up with something that's greater than 2m, okay, because all of the powers are less than m themselves. Okay, so when you add two of these powers together, the worst possible scenario is that you get between m and 2m, basically. So this really is a plus b is greater than m but less than 2m. Okay, it can't ever get above 2m simply because these are the only powers we've got, basically, and they're all less than m. Okay, so all you need to do is factor out 1x to the power of m and then get whatever the remainder is here, and then that's your answer, basically. Okay, right, so that's how we compose any two elements together, okay, and that hopefully shows you that this is indeed closed, because I've now shown you, if you take any of these two elements here, how to compose them together to get another element that is within this set, basically. Okay, so it is closed under composition. We don't need to worry about associativity. Never ever do we need to worry about associativity when we're dealing with subgroups, so we'll just cross that one straight off. We have an identity element because x to the power of naught is representing the identity from the original group. And indeed, with our composition law that we've got here, when you compose x to the power of 0 with any of these other powers, you'll just end up with that other power back again, and that's true whichever way round you compose them. Okay, so that's all good. We've got an identity element. And then the other one, the important one now, inverses. We need to have inverse elements. Okay, and it's not instantly obvious that you do have inverse elements. Okay. So, we didn't, remember in the case of the infinite cyclic subgroups, we had to put in x inverse, we had to put in all powers of x inverse. Why have we not had to do the same thing here? Well, I claim we already have inverses, and this is because of the fact that x to the power of m is equal to the identity element, is equal to the x to the power of 0, basically. Okay, and I keep changing my notation for the identity. I do apologise. I'll replace that with e. Let me just rewrite that out. Okay, so e here, it's the identity element. Okay, right. So, why does that help us? Well, if you want to find the inverse for any element in here, all you need to find is the complementary power of x, that if you add that power to your power, then you will end up with m, basically. Okay, so let me do an example. So if I want to find the inverse for x to the power of 1, okay, what can I do? Well, I can find the other power of x, which if I add it to 1, gives me m. Now that's obviously x to the power of m minus 1. Okay, so if I compose x to the power of 1 with x to the power of m minus 1, what do I get? Well, I have to add the powers together, so what I'll end up with is x to the power of m minus 1 plus 1, okay, which is just x to the power of m, which of course is just equal to the identity element. Okay, so that means that x to the power of m minus 1 is x to the power of 1's inverse element, basically, and indeed x to the power of 1 is x to the power of m minus 1's inverse as well. Okay, and you can do that for other elements as well. You just have to find the complementary power that together they add to give m, basically, and therefore the identity. Okay, so that's why this has inverse elements in, because of the fact that x to the power of m is equal to identity, which is never true in the case of infinite cyclic groups. That's why you needed all of the inverses added separately in the infinite cyclic subgroups, basically. Okay, whereas here you don't, because this is suddenly true. Okay, right. So that now proves that these things are indeed subgroups. So that's how you create these finite cyclic subgroups then. You take your element x, you start by putting the subset where you have the identity, and then you put in x, and then you just generate all powers of x that are distinct until you get up to some power of x, which returns you back down to the identity, and then you stop. Then you're completed, and I've just shown you that for an arbitrary group, for an arbitrary element, little x in that group, that this works and forms a subgroup, and that is called the finite cyclic subgroup generated by x, or just the cyclic subgroup generated by x. Okay, right. So the next thing to do then is to prove that these finite cyclic subgroups are isomorphic to finite cyclic groups. Okay, so my claim is that this finite cyclic subgroup that I have here, which has, by the way, a little m elements, so let's just count up how many elements there are in this finite cyclic subgroup. So there is a little m minus 1 powers of x here, and then we also have the identity here, which is 0, so that takes us up to little m elements in this group. Okay, right, so if I'm going to claim that this finite cyclic subgroup is isomorphic to a finite cyclic group, which finite cyclic group am I going to be able to claim that for? Okay, well, it can only be the finite cyclic group on m elements. Okay, so C a little m. Okay, because only that group will actually have the right number of elements. Okay, if we're talking about isomorphism between two finite groups, then the two finite groups need to have the same number of elements. Okay, so I'm going to claim that this is isomorphic to the cyclic group on m elements. Now, hopefully that should be kind of obvious to you, because the way that I compose the elements here is identical to the way that I compose elements in the finite cyclic group Cn, basically. So let me just remind you of the finite cyclic group Cn. Okay, so remember, this consists of the identity elements, okay, then it consists of sigma, and then all powers of sigma up to sigma to the power of n minus 1. So sigma squared all the way up to sigma to the power of n minus 1. Okay, if it helps you, replace the identity once again with sigma to the power of 0, okay, and sigma with sigma to the power of 1. Okay, and if we remember how we compose elements together in these finite cyclic groups on m elements, the way that you do it is simply by adding the powers of sigma together, okay, and then if you end up with a power greater than m, you get rid of the bit that's you get rid of the sigma to the power of m, you factor out the sigma to the power of m, acknowledge that that is the identity once again, okay, and then just take the remainder, which is exactly what we do here. Okay, so quite simply, the isomorphism between these two is simply the relabeling map that relabels x with sigma, basically. Okay, just relabel up all of these as sigmas rather than x's, and you've turned it into this, and then the composition law is just identical, basically. Okay, so I hope it should be intuitively obvious that those two are isomorphic to one another. Okay, right, so we've now seen then cyclic subgroups, and we've seen that you can have finite cyclic subgroups which are isomorphic to finite cyclic groups, and we've seen that you can have infinite cyclic subgroups which are isomorphic to the infinite cyclic group, which is the group of integers under addition. Okay, the final comment that I just want to make is the sort of formal definition then of what a cyclic group actually is. Okay, and the formal definition of what a cyclic group actually is that it contains an element which is actually capable of generating the entire group. Okay, and what I mean by that is that if you took the cyclic subgroup generated by that element, then it would generate the entire group. Okay, so this is the way that people often define cyclic groups. Okay, so I'll just put this down here. So cyclic groups, both the finite and infinite cyclic groups, what they contain basically is they need to contain an element x. Okay, and I'll just denote cyclic groups arbitrarily as C for now. So and there needs to be an element, little x, which is an element of C, such that if you generate the cyclic subgroup generated by x, this is actually equal to the entire group, basically. Okay, that is a property that these cyclic groups have. They have an element within them that if you generate its cyclic subgroup, it actually is equal to the entire group. Okay, so in the case of all of these finite ones, it is just sigma to the power of 1, basically. If you use sigma to generate a cyclic subgroup, you would get the entire group back again. Okay, in the case of the infinite cyclic group, which is the group of integers under addition, it is 1. If you consider what the cyclic subgroup generated by 1 is, that will consist of 1 composed with itself an arbitrary number of times. So you'd end up with 1, you'd end up with 1 plus 1, which is 2, you'd end up with 1 plus 1 plus 1, which is 3, you'd end up with the inverse of 1, which is negative 1, and all numbers of compositions of negative 1. So if I just draw this out, you'd start by putting in the identity, which is 0, you'd then have plus 1, okay, and you'd have plus 1 composed with itself an arbitrary number of times, which would give you plus 2, plus 3, plus 4, and on, okay. You'd then have to put in the inverse of plus 1, which is negative 1, and you'd have negative 1 composed with itself an arbitrary number of times. You'd have negative 2, negative 3, negative 4, etc., like so. Okay, and therefore you'd end up with the entire group of integers back again. Okay, so once again, the group of integers can be generated by a single element, basically. Okay, it is effectively if you take the cyclic subgroup of a single element, you can get the entire group back again. So that's another way of viewing cyclic groups, that they are equal to the cyclic subgroup generated by a single element, whereas a non-cyclic group, there is no such element that you could find which, when you take its cyclic subgroup, would actually generate the entire group. Okay, right, so that now concludes our discussion of cyclic groups and cyclic subgroups.